Ahoy there, land lovers! Welcome aboard! Water might seem like a really boring liquid, but actually it has some very unusual properties. So come and dive in as we submerge ourselves in some watery science, explore H2O, how things float like a boat or sink like a submarine, or even how little insects can skim across the top of a pond. As we explore the world of water today, you might want to get your kitchen ready for some aquatic action and find some equipment to help you along the way. You're going to need a jug for some water, a glass, a bowl, a penny, a pipette or a straight straw if you don't have a pipette, some pepper or herbs or glitter, some soap, a fork and a paper clip, a little bit of foil and a pair of scissors, a bendy straw, some toothpicks or cocktail sticks, a plate, a paper flower template, some plasticine. Water is a very unusual substance. It exists as a liquid at most temperatures that we find here on Earth, but lots of other substances have to either be heated or cooled in order to be a liquid. In fact, 2/3 of our Earth's surface is covered by the oceans, and that's excluding the water that runs in streams and rivers and in lakes. Water can also exist in other forms. So at the top of mountains and at the North and the South Pole, it's solid in its form as ice. Water can also exist as a gas way up in the sky in our atmosphere as water vapour, forming clouds. Water is constantly evaporating from our seas, rising up into the atmosphere as water vapour. And as the clouds build up water vapour, it often returns to the seas in the form of rain. This water has created the landscape that we can see today by eroding the surface of our planet over millions of years. And water plays a significant role in supporting all life forms on our planet. All plants and animals need water in order to survive, and those that live on dry land get their water from the soil or from rivers and lakes. We use water every day and collect it to drink from it, to wash with it, and we even use it to water our crops. Our bodies are actually 60% water. So let's have a look at this water in more detail. So what actually is water? Well, let's imagine if we could see water really close up. It would look something a bit like this. So this is a model, and scientists like to use models to help them explain and demonstrate particular things. Now, everything around us exists as molecules, and they are atoms that have been put together to make a substance. This water molecule has 2 hydrogen atoms, that's what the H's stand for, and 1 oxygen atom, O. And if you've heard of H2O before, that is what the molecular formula for water is, H2O. So water is one of the most abundant substances we have on our planet. That means there's an awful lot of it. Wouldn't it be amazing if we could split it up and turn it into a fuel? Well, this is actually what scientists have researched, breaking up a water molecule into hydrogen and oxygen. But we would need even amounts to do this, because an hydrogen atom can't exist on its own. It would have to go with another hydrogen. So then the oxygen would be all on its own. So we would need another water molecule to break up and put together. So we would take 2 water molecules and from it make 2 hydrogen molecules and 1 oxygen molecule. And the hydrogen can be collected and used as a fuel. In fact, hydrogen is the most used fuel to launch a rocket. And when hydrogen burns from a space rocket, it combines with oxygen in the atmosphere to go back to form water again. So it creates a huge amount of energy and makes heat and light, but the end product will be water. Instead of combusting hydrogen like inside of a rocket, scientists have now developed a fuel cell that can use the chemical energy stored inside of hydrogen to power cars. The only problem is it takes a huge amount of energy to split a water molecule into hydrogen, and this energy we're currently getting from combusting fossil fuels. Unfortunately, hydrogen won't be a clean green energy until we can find a renewable way that uses less energy to split water into oxygen and hydrogen. Research continues in this particular field to try and make cleaner energy for our planet. Imagine if the only waste product we get back is water. Let's explore the unusual properties of water. So here we have a simple glass of water, and we can see that light is travelling through the water just as it can travel through air. But in fact, light is travelling differently because it's a liquid. And we can show this by adding a little rectangle piece of card behind the glass. And as you look through the glass, we can now see that this rectangle is curved. The water is reflecting the light in such a way that it looks like this piece of card is now curved. If we take a straw and insert that into the glass of water, we can see that the straw looks to be in a different position below the water than it is above. So this is the unusual effect water can have on light. Water molecules really like to stick together. If we look at the water in this glass, on the surface of the water, the molecules have much more of an attraction for the water molecules below the surface than the air above. And this gives water an unusual property called surface tension. And that's where the surface of the water are pulling all the molecules inward and give it this stretchy skin. We can test the strength of this skin by overfilling our glass. So if I take more water and keep pouring it in, we're going to keep pouring, and as we do, we can see the surface tension bubbling up right to the top. This surface tension is stopping the water molecules from breaking apart, and with every extra drop, we can see the surface tension pulling the water molecules inwards, holding it together like a skin. You can do a similar experiment on the surface of a penny and see how much water you can fit on top before the surface tension gives up. We're going to need some water and a pipette if you've got one, or you could use a straw and dip your straw in, cover over the end of the straw, and then drop the water onto the penny. So we're adding the water drop by drop onto the surface of the penny, and with every drop we add, we can see the surface tension trying to hold it together until it gives up. Some tiny insects, like water boatmen, sit on the surface of the water without breaking the surface tension. We can try a similar experiment using a paperclip. So if you try to put a paperclip to float on the water, usually it will sink to the bottom. But if we place that paperclip down very carefully and gently, we can get it to rest on the surface. So I'm going to use a fork to help me, and I'm going to rest the paperclip on the fork, and I'm going to very carefully lower it onto the surface of the water. And as I do, we can see that it has managed to keep that surface tension intact. And the stretchy skin of the water hasn't been broken. These water molecules on the surface try to hold on to each other so strongly that we can actually pour some ingredients on top. So this is a bit of pepper, and instead of it sinking to the bottom, it's light enough to sit on the surface without breaking the surface tension. So I'm going to sprinkle a good amount of pepper onto the surface. And we're going to see how strong this surface tension is. Now that the pepper's sitting on top of the surface of the water, we're going to see what can break the surface tension. And one of the most common products we use at home is soap. So I'm going to dip my finger in some soap. I'm just going to touch the surface of the water and see what happens when the surface tension breaks. Any kind of herb or even glitter would work. A pond skater is a very light insect that can spread its weight across its legs and sit on the surface of the water, just like the pepper, the herbs and the glitter did. In a similar way, we can create a very light boat made from foil. So I've taken a little bit of aluminium foil and cut out this boat shape. And the important part of this boat shape is to make a little slit at the back end with a hole large enough to be able to drop a bit of soap in. So we're going to place the boat on the surface of the water without breaking that surface tension. We're going to use soap like we did in our previous experiment, but this time, instead of dipping our finger in, we need to make sure that the soap lands in that hole at the end of the boat. As we dropped the soap on the edge of the boat, we could see it move. As we add soap to the water, it disrupts the surface tension behind the boat, but the molecules in front of the boat are still pulling together, and that's why the boat's pulled forward. This amazing property of water's surface tension doesn't just happen at the surface of water. In fact, it helps water droplets to stick together so that when rain runs down the window, it will form lines, and when you turn the tap on at the sink, you'll get a nice column of water. Another way we can show this is by pouring water down a piece of string. As I gently tilt the jug, the water starts flowing down the string instead of falling straight down with gravity. I can even extend the piece of string to make it travel further away. The friction between the water and the string is enough to pull the water molecules together and let it travel down. Next, we're going to have a look at a method called siphoning. And siphoning happens when we've got two different levels of water. So here we've got a bit of coloured water just to make it a little bit easier to see. And this glass is filled nearly to the top. And then we've got a bowl of water with a much lower level. I'm going to take a bendy straw and I'm going to submerge the straw in water to get rid of any air bubbles. So you could do this in a sink or a bucket, and we just want to make sure that all the air is out of the straw and it's now filled with water. I'm going to pinch both the ends of the straw to keep that water trapped inside, and I'm not going to let go of those ends until they're back in these two water. Now you'll notice that this is siphoning really nicely from the higher level and coming out to the lower level of water. And it's got more potential to move because gravity is helping. But don't forget, surface tension is involved here as well, as all those water molecules are sticking together and allowing the water to come out. This will continue to happen until the levels are equal. And at the point that both the water levels are equal, it will stop siphoning. And that's because the potential energy is the same. Many materials in our homes absorb water, and when they absorb, they expand. And we can see this effect with some cocktail sticks. I've got 5 cocktail sticks here, and I'm going to snap them in half, but I don't want to completely break them. I want to make sure that they just kind of fold like this. And I'm going to put them on a dry plate and arrange them into a star shape. If we add water to the centre of the star, the cocktail sticks absorb the water and begin to move. It makes the wood expand and the broken ends press against each other so that the toothpicks open up. This property of wood absorbing water has the same effect on our wooden doors in our homes. When we've got really high humidity in our homes, the wood expands and gets stuck in the doorways, making it difficult to close or open them. As you well know, there are many other materials in our homes that absorb water. It's not just wood, but other materials can absorb it quicker or have a spongier effect. So we're going to use paper in this particular activity, and I've got a paper template you can use. I'm going to cut this flower out and we're going to fold over the petals of the flower. As I fold them over, I'm just turning the flower around and they're all going on top of each other. We're carefully going to place that into the centre of a plate of water and see what happens. So the paper flower floats on the water, but because paper's absorbent, it's now expanding. As the paper absorbs more and more of the water and it continues to expand, we can see that the petals start to get pulled down. Different objects act in different ways when they come into contact with water, and some objects sink whilst others float. So here we've got a little bit of plasticine, and if I drop it into the water, you can see it goes straight to the bottom. But if I take this plasticine and change its shape, we can change how it behaves on the water. So we've moulded the plasticine into a larger surface area. And if we now gently place that on top of the water, we can see it floats. It's not changed in weight, it still weighs the same, but what has changed is the area in which the water is in contact with it. An increased surface area means there's more pressure acting on this piece of plasticine. And this is really important when we're looking at designing boats. The hull of the boat needs the water pressure underneath it to support its weight. As you go beneath the surface, the weight of the water above presses down and this creates pressure. This is the same pressure that ensures water comes out of your taps. In fact, only 100 metres below the surface of the water creates enough pressure to feel like a person standing on every square inch of your skin. So submarines that dive to the deep depths of the ocean need to be incredibly strong to survive this amount of pressure.